Okay, so today's lesson will be about commutators. So we all know that multiplication of ordinary numbers does not depend on the order in which you do it. For example, if I take 3 times 5, that's the same thing as 5 times 3, and it's equal to 15. So it does not depend on the order in which you multiply 3 and 5. And in this case, we say that the multiplication is commutative. So commutative just means that it doesn't depend on the order in which you do it. But at higher levels in math, we encounter objects where the order of the multiplication does matter. So where A times B may not be equal to B times A. And when this happens, we say that A and B do not commute. So where in math does this happen? Well, there's actually a lot of examples. So the simplest example is where A and B are just matrices. And this happens in linear algebra. A more complicated example is where A and B are operators on a Hilbert space. And this example you find in quantum mechanics. And there are actually many other examples. So, when A times B does not equal B times A, we might want to understand how badly they differ. And for this, we define the commutator of A and B. So, what is the commutator of A and B? Well, it's written with this square bracket notation, A comma B, and it's defined simply as the difference of A times B minus B times A. And if A times B is equal to B times A, then the commutator is equal to 0, but otherwise it's not 0, and it gives us useful information about how A times B differs from B times A. So to close this video, we're going to look at a simple example of objects with a non-zero commutator, and we'll look at an example with matrices. So for this example, we need to choose two matrices, A and B, and I've made a simple choice here. So I'm going to take A to be the matrix 1, 0, 0, minus 1, and B to be the matrix 0, 1, 1, 0. So these are two 2x2 matrices. And now we can calculate their products using the rules of matrix multiplication, and you can check it at home, and you'll find that A times B is equal to 0, 1, minus 1, 0, but B times A is equal to 0, minus 1, 1, 0. So if we now calculate their commutator, which remember is just the difference A times B minus B times A, we'll find that it's not 0, but it's this matrix 0, 2, minus 2, 0. And so it does not vanish. So there you have a simple example of two objects, A and B, that have a non-zero commutator. And that's the end of this lesson.